Hi guys, my name is Elizabeth and today we're going to be going over the Broglie waves. So here it says, what is the wavelength of a neutron traveling at a speed of 4.15 kilometers per second? So the first thing you need to think about is which equation you're going to use, because this chapter is very, very heavy on equations. But I'm going to give you a little secret. If they give you the velocity or the speed of something, you automatically should be thinking of de Broglie's equation. So I'm going to go ahead and write that on the board for you. De Broglie's equation is that wavelength, or lambda, is equal to Planck's constant, h, over m, which is the mass, times v, which is the velocity. So Planck's constant is a constant that we used before in one of our other equations. So this is actually going to be 6.626 times 10 to the negative 34 joules times seconds. Our mass is either going to be given to us, even though in this problem it doesn't seem like it, but I'll explain that in a second. And our velocity is also given to us. So we're actually solving for this guy. This is our unknown. Right, because we're solving for wavelength. And they gave us our velocity, but our velocity needs to be in meters per second. So let's deal with each one of these individually. So let's deal with mass first. In the problem it says that I'm doing number 57 in your book, and it says that the masses of the electron, proton, and neutrons are in the back cover of the book. So I just looked there and I found the mass of the neutron. So I know that my m is going to equal 1.6749 times 10 to the negative 27 kilograms. And then our velocity, we need to be converting that. So that means instead of kilometers per second, we need it in meters per second. So the only thing I need to do is convert the kilometers to meters. So I'm going to start off with the 4.15 kilometers, and I'm going to convert that to meters. So if kilometers is on top, it needs to be on the bottom, and I'm converting it to meters. I know there are 1,000 meters in 1 kilometer, so that gives me 4,150 meters. And that's what's going to be plugged into here, and it's going to be per second, just because the seconds didn't change. So let's go ahead and plug those in and see what that looks like. So we're going to have our wavelength is equal to, we have Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, all over. We have our mass, which we got from the cover of our book. So 1.674 times 10 to the negative 27 kilograms. And then we also have our speed, which is going to be 4,150 meters per second, which is ridiculously fast, but that's fine. They're very small. They can do those kinds of things. So when you plug all that into your calculator, you're going to find that you get 9.53 times 10 to the negative 11, and that's going to be in meters because this guy's in meters. Alright, but usually they don't want it in just meters, so I went ahead and converted to nanometers because that's usually what wavelength is measured in. So that's also going to be 0.0953 nanometers, and all I did there was just multiply by 10 to the 9th. And then that's also still a little too small, so if I were to do picometers, it would be 9.53 picometers, which seems about right. So to recap, when I see this problem and I see that they gave me velocity, I automatically thought to use de Broglie's equation, just because that one is the only equation that we have that deals with velocity. So it's like this not so fancy v, not like the mu, the frequency one, but this one has to do with velocity. So in this problem, they'll give you mass and they'll also give you a speed. So it'll be very easy to just plug it in because you know Planck's constant, and you can solve for wavelength. So yeah, that's how you use de Broglie's equation.